Welcome to part 3 of our exploration of predicting reaction types SN1, SN2, E1, E2, and NGP. We have a molecule here with a leaving group. It's not obvious, but that is the short form for toluene sulfonate. That leaving group over here will look like this. Toluene sulfonate has a minus charge. It is the conjugate base of toluene sulfonic acid. The conjugate base of any strong acid is an excellent leaving group. What's going to happen under these circumstances here? We have a secondary carbon with our leaving group. That is ambiguous. We do not know if it's SN1 or SN2 in either of these two examples. Same molecule. Nucleophile is the same in the two examples as well. It's a strong nucleophile, which usually causes an SN2 reaction. So we are leaning now towards an SN2 reaction. The solvent here, dimethyl sulfoxide, DMSO, CH3 twice, S double bond O, is polar aprotic, which also leans towards an SN2. Down here, we switched it over to ethanol, which is polar protic. That is an SN1 solvent. Seems like we have conflicting information here. I usually consider that unfair. Which way do I want the students to go? But there's more going on there than just these two things. We'll see that when we get down there. Right now we've got two things. One of them saying SN2 here, and another one saying the same thing. We're definitely thinking SN2. Nucleophile and solvent participating towards that decision. SN2 involves a backside attack by this nucleophile on this stereocenter. So when we're finished, the H gets pushed outwards, and the nucleophile is going to be here, OET. It didn't ask us to draw the whole thing. ET is a good common short form. And that would be the product right there. We've generated an ether here. This is a good way to make ethers. The name of this reaction, if you are into naming things like this, is the Williamson ether synthesis. And that concludes that one. Down here, we have all the same analysis. We've got a change in our solvent, however, but that is superfluous compared to the fact that we now have a strong nucleophile that's also a strong base with a pKb of -2, considering that ethanol is the conjugate acid of this base. Ethanol has a pKa of 16. pKb of this is -2. And that is not the only factor that contributes to our conclusion. Any strong base combined with heat as well will give this override called bimolecular elimination. Bimolecular with a 2 and elimination with an E. We're going to be making a pi bond. Our leaving group's going to be gone, and a beta hydrogen's going to be gone. We better talk alpha and beta shortly. All right, how's that for shortly? We've got our molecule here with a strong base poised to grab a beta hydrogen, and what's going to happen is an E2 reaction where the lone pair grabs the beta hydrogen. The sigma bond between the hydrogen and the carbon collapses down to make a pi bond. And our leaving group does what leaving groups do. It leaves, giving us the major product here. We have made what is called a tri-substituted alkene. It has 3 carbons attached to the alkene, which is very highly substituted, has lots of hyperconjugation, and we don't have to show our leaving group. It wasn't asked for here, and that would be the major product. There'll be 2 minor products resulting from the removal of this beta H, and I will draw the obvious one first. I drew it over here. A more stable alkene would be the one where we have an E alkene. When the ring is large enough, we can make an E alkene. It's not the prettiest looking here, but definitely seeing E now. And that would just result after sigma rotation of this carbon and grab the other H. You weren't even asked to distinguish the two minor products anyway, so if I see one and the other, that's fine. Over here you're making the argument, why didn't you draw the E version of this one? And my answer to that is, in another video exclusively about bimolecular elimination, you learned about the anti-coplanar relationship of the beta H and the leaving group. The leaving group's right here. If they're anti-coplanar, the reaction happens smoothly and quickly. If they are not, if they are syn, then it's not a fast reaction. And for an E product to result, you would have to do sigma rotation here, and that would bring the H outwards and the methyl back, and it would be syn coplanar, which is a much slower reaction. You could draw the product, you'd probably get a point, but really it wouldn't happen. And once again, mechanism's not really part of the question here. Those are on a separate part of the test. So this would be the results I am looking for full credit. And this concludes our video, Predicting Reaction Types Part 3. I strongly encourage you to also watch the video about bimolecular elimination. And I look forward to our next video.